Today's topic is a beam on elastic foundation. Beams on elastic foundation. This is a very classic topic, and it's an extension of beam theory. Okay, so we need to give some modification for beam theory that we can solve the problem here. So topic is beam on elastic foundation. Okay, in the engineering practice, we can meet this kind of problem a lot. For example, let's say, before giving you example, I like to describe the problem first. So here we have a beam. I put this beam on some foundation. So you can think you put the beam on the soil, okay? And y is a vertical axis, x is a horizontal axis, and this is beam, and this is an elastic foundation. So elastic foundation behave like a spring. If we push the foundation, it gives us force to my finger. Okay, so and applied load is this is applied load. Okay, so this is our problem. And B measure displacement. This is B measure displacement, B displacement. And elastic foundation have a stiffness K. Stiffness. And this is a unit is force per displacement per length. Okay, so I like to give you a practical example. Let's say this is a building we have. Okay, to support this building, we need to make some foundation here. This is a building, and this is foundation. Actually, this is this is a foundation structure. Foundation structure, and this. So we build the building or any structure on the foundation structure. So you can think this is something like a mat, big mat. And here we have a soil or rock. Okay? So this foundation structure is actually beam, behave like beam. And this soil or rock, earth, surface of earth, is an elastic foundation. And also the other example is a floating structure. Here we have a still water and floating structure here. Okay? And this water is an elastic foundation. And this floating structure is a barge or ship is a beam. Can act like beam. Why this water is can be modeled by elastic foundation? Why? You know? Buoyancy, the definition of buoyancy is that G okay, G and density of water, and okay, this is a submerged volume. So submerged volume can be calculated by P, the breadth, height, and width, right? This is submerged volume. And this can be rearranged like this, B, W, H. H is the depth. If you change the depth, so V. This V is, you can think this V is force, H is displacement. And this is a spring constant. So buoyancy can be modeled by spring. This is K. Okay, so the theory for beam on elastic foundation can be used to calculate the moment and displacement of a beam-like floating structure. So this problem, okay. Now let me give you, okay. Let's say this is y-axis and x-axis. Okay, and so profile of beam it looks like this. This is profile of beam. So then this is a deflection. This deflection gives the force in this direction. The amount of force is K Vx. Vx. And you can think like that. Here I have a beam, and here a lot of spring. So beam is supported by spring. Actually, this is not a simple spring. Distributed spring with a spring constant K. And if this beam is deformed like this, okay, from the equilibrium point, this distance is V, and because of this distance, there's going to be a spring force KV. Understand? So governing equation for Euler balloon equation beam theory was that DEI DQB minus Q. This is a governing equation for Euler balloon beam theory. Beam theory. You remember? And Euler beam theory, we consider only distributed load Q, but this spring force is also distributed load. Okay? Direction is minus y direction, right? So here, instead of Q, EI dx square, d square b minus Q. Here we have a Q and plus KB equal 0. So we only add one term in the original equation, beam equation, to give governing equation for beam on elastic foundation. So the governing equation is changed a little bit. And when EI equal constant, the equation become B plus EI KB equal EI Q. So we have a simple, ordinary differential equation. Looks like that. So when we model floating structure, especially for hydrostatic case, it means there is no dynamic motion. We are using that equation to solve the displacement and moment of the floating structure. So let me think about a solution. First, homogeneous solution. So homogeneous solution is a solution of this equation K E I V equals 0, right? You know the meaning of a homogeneous, right? Homogeneous solution. And to solve this equation, usually we assume V is E beta x. And if we put this equation into here, we can have an equation about beta, right? And we can solve this equation. Okay, so not the beta, let's alpha, same thing. Okay, then we can have a solution, homogeneous solution BH equal E alpha x C1 cosine alpha x plus C2 sine alpha x plus E minus alpha x C3 cosine alpha x plus C4 sine alpha x with alpha equal 4 square root K 4EI. This is a homogeneous solution. So we have an exponential term and sine and cosine terms. So for this kind of ordinary differential equation, the solution is sum of homogeneous solution and particular solution, right? This is basic mathematics. And second, particular solution. So particular solution depending on Q, right? Particular solution depending on Q. So when we set the right hand side Q equals 0, we can have a homogeneous. Okay? And let's consider when Qx is Q0, constant case, the simplest case. The particular solution is V particular is a Q0K. You can check this is a solution or not and put this solution into the ordinary differential equation. So finally, in this case, general solution equal B equal B homogeneous B particular. This is general solution. So this general solution have a constant, integration constant, right? So to find out that integration constant, we need to apply boundary condition. Force boundary condition and displacement boundary condition. So actually, to find this solution is not that hard. I mean, you have a lot of tools. Even you don't know the theory about solution method of ordinary differential equation. If you know how to use the mathematical or Maypool, you can easily find the solution, right? But the choosing properly boundary condition is very important. It can be done by your engineering decision. Okay? So engineering sense is very important to find the boundary condition. So I'll give you example. Let's consider beam. This is a beam and elastic foundation here, and y-axis, x-axis, and this beam is have a infinite length in x direction and minus x direction. Okay, and at x equals 0, point load P0 is applied. So I like to solve this problem. So I wanted to calculate the displacement for this problem. Then we can automatically calculate moment and stress, right? So this is an infinite beam. And point load P0 is applied at x equals 0. Okay? So let's look at this. Point load is applied at the center. And this is symmetric problem, right? So solution of this side, right side and left side is symmetric about the x. Solution is symmetric about the x equals 0, right? So in this kind of symmetric problem, we don't need to consider whole domain. We can only consider half of the domain. So let's change. Let's consider only half, something like that. Then problem becomes simple. Y, and here x equals 0. Let's consider only this domain. Then here we need to consider, instead of P, the point load is P0, half of the P0. Okay, this is important. So half of the load is supported by right part, half of the load is supported by left part. Okay, so we need to use only half. So we only consider x, domain x equal bigger than 0. Okay, and in this case, distributed load is 0. When x is bigger than 0, q is 0. Distributed load is 0, so particular solution is 0 too. So we don't need to consider particular solution. Okay, and then this case the general solution is it become V equal E alpha x C1 cosine alpha x. So general solution. Okay, not that. Plus C2 sine alpha x plus E minus alpha x C3 cosine alpha x plus C4 sine alpha x. So now we need to find only 4 integration constants because we don't need to consider particular solution. Then now let's talk about boundary condition. This is a quite hard job. So first, displacement boundary. So, 정호, you have idea about the displacement boundary in this case?
When x equal infinite, the displacement is 0.
Right. So load is applied here. So at this point, there are going to be a maximum displacement, but x increase. Okay. So let's go to the plus infinite. Then finally, displacement will be 0. Right. That's one of the boundary conditions. So when x go to plus infinite, Bx go to 0, right? Right? And finite cannot be infinite, right? 0 means finite. It has some value. And how about the other boundary condition? Can you identify other boundary condition in this problem? This is a beam problem. So displacement will be one is a y-directional transpose displacement, the other will be a rotation. So in this kind of symmetric problem, okay, at the center, so for example, deflection will be something like this, okay? So x equals 0. The displacement is symmetric. But it means at this point, no rotation. Okay? No rotation. So, no rotation means slope of displacement is 0. So, rotation theta 0 equal v equal 0 equal 0. This is a displacement boundary condition. And force boundary condition. So now we have a two boundary condition, force boundary condition. So when we can know the force, is there a point we can know the shear force or moment? Can you find here? Yeah, let's consider here this part. We can calculate the shear force. So shear force, so at V0 equal P0 over 2. V0. So at x equals 0, we have a shear force. So at that x equals 0, here x equals 0. This is the externally applied load. 2P0. This is internal load. 2P0. Due to the sign convention, this is a plus, right? Plus shear force. And this equation means V0 equal minus EI and x equal 0 equal P0 over 2. So now we have these three boundary conditions. Do we need more? More or not? Okay. Then let's apply the boundary condition. How about the first boundary condition? Let's increase x. Let's x go to the plus infinity. Here x is here. This is x, 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 x. So cosine x, sine x, cosine x, sine x. So range of this cosine is from -1 to +1. How about range of sine? -1, +1. How about this here? If x increase, this exponentially increase, right? Go to the infinity. How about this one? Decrease, exponentially decrease. So this boundary condition means this term should be 0, right? This is not meaningful, right? Physically meaningful. So it means C1, C2 should be 0. From here, first boundary condition, C1, C2 should be 0. Okay? And then, let's consider next boundary condition. Let's take the derivative of this term about x. Then here, minus term like minus sine C3 minus sine alpha x here, C4 cosine alpha x, and then put x equals 0. Okay, then from the second boundary condition, we will find out C3 equals C4 to satisfy the condition here. Okay, then now we need to determine one of these, C3 or C4. Then we can use false boundary condition. Okay, then to apply the false boundary condition, we need to differentiate that displacement 3 times, right? And put x equals 0. So then finally C4 equal minus P0 3 8 EI alpha cubic. This is C32. So finally solution equal minus 2K P0 alpha E minus alpha x cosine alpha x plus sine alpha x when x equal positive. This is solution. So if I plot this, the shape looks like this: x, y. Okay. Here, no deflection, no rotation. The slope is 0, and it decreases. Something like that. This is solution. And at this point, B0 equal minus P0 alpha 2K. This is symmetric. So the other solution for negative x is similar. Something like that. So there are some observations. Displacement vibrate, right? And the magnitude becomes smaller and smaller. And finally, will be 0, disappear. Okay? And length of this depends on the stiffness of elastic foundation and alpha. Alpha includes stiffness of bending stiffness of beam. Okay? And when for negative x, when x is smaller than 0, by symmetry Vx equal minus P0 alpha 2K E alpha x. cosine alpha x minus sine alpha x. So if you put the minus x here in this equation instead of x, you can have a solution for left part of beam on elastic foundation. And finally, considering left and right part, we can have a solution P0 alpha 2k E minus alpha absolute value of x cosine alpha x plus sine alpha x. This is a final solution here. Okay. So, any question? So, I like two interesting example, practical example. Here I have a floating structure. It's quite steep, and the other one is not steep, very thin. So EI 2, EI 1. EI1 is much bigger than EI2. For the first case, displacement looks like this. So actually here some point load is applied, P02. So P0. At P0 is applied, here P0 is applied. Length of the beam is same. Length of the beam is same. In the first case, deflection will be like this. Okay? Second case, deflection will be like this. It's different, right? So, solution of first case will be part of the solution from here to here. Okay? And second case, solution is a part of the solution from here to here. When the K is fixed, okay, solution is totally looks different. So some people don't understand. So in this case, okay, how can we have this kind of vibrated displacement? But we can have. Okay? So people always think solution always look like this. And people don't understand this kind of solution. Okay? Many engineers think this is not realistic. But this is realistic. Okay, so let's finish the lecture today. So any question?